So one question that you're probably asking yourself is, are we ever going to talk about the second derivative? Does it have any role to play here? And the answer is yes, it does, and yes, we are. And I thought it would be best to introduce the ideas to you with a picture first, and then we'll look at some actual definitions. So let's think about this picture together. Here's a nice curve. This is going to be f, and I just want to draw some tangent lines with you. Let's draw them pink. So at this point, right there, you can kind of get a sense of the tangent line. Oops, okay, you know what? I'll draw the tangent lines first, and then I'll decide where the intersection point is going to be once the iPad makes it straight for me. So yeah, we'll do that one is like right here. Okay, and what do you notice? Compare that tangent line with this one. Hopefully we can make this work. That's not tangent at all, actually. I'm just going to have to freehand them here. So what do you notice about the difference between these three tangent lines? So this one, there's a tangent line, to this one, to this one. What's the slope of the tangent line doing? It's dropping, it's decreasing, it's getting less and less. So first off, notice it's positive, positive, positive. All of a sudden right here at this point, there's a local extrema there. Wow, I can't draw today. That's okay. And actually the slope is, oh my goodness, the slope is going from being positive to less and less and less. Now it's 0. And now on this side, the slope is actually negative. It's negative, negative, negative. And make sure that that's clear to you what we're talking about. If you need to pause the video, please do so. And then I want you to notice, though, that something happens, and it's difficult on a hand-sketched graph to, or to any graph, actually, to precisely say where it happens. But something happens. We're decreasing, 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 and then all of a sudden, the slopes are climbing again. Do you see? Somewhere right in here, let's say right there, we're going to mark that as a line. The slopes go from getting smaller and smaller and smaller, where there's a point where it freezes. And then on this side, look at this slope. Let's look at this slope. Man, I'm struggling to draw these lines. Let's zoom in a little bit. Look at that slope. Okay, this is supposed to be right there versus this slope. Okay, and you can see that, oh, that slope's bigger versus this slope. That's actually 0. So this is a negative slope. This is a much less negative slope. This is a 0 slope. And now over here, we're climbing again. Does that make sense? And so that, what we're studying here is what's called concavity. And I want to go ahead and introduce the terminology to you right here, right now, before I write anything out fancy. So on this side of this particular point, we're going to call F is going to be concave down. All right? And a couple of takeaways that you can notice from that. First off, tell me about the slopes of the tangent line. They are decreasing, right? The f prime of x is decreasing. So concave down seems to mean that the slope of the tangent line is decreasing. Okay? And secondly, what other phenomena do you notice? Look at the relationship between the tangent lines and the graph. This may be a little hard to tell. I think you can see it. All of my tangent lines lie above the graph. Do you notice that? Every tangent line is sitting on top of the graph. On this side, the tangent lines are all below the graph. And so here, let's go ahead and write that down. So the graph of, I'm always going to say it in terms of the graph of f. So the graph of f is below tangent. Below the tangent line. So concave down seems to mean that the graph of f is below the tangent. On this side, f is concave up. And you can see that f prime is actually increasing. And you can see that the graph of f is above the tangent line. The graph of f is sitting on top. The tangent lines are all sitting below. So with that example in mind, I hope that helps illustrate the following definition. So this is a little more formal. So we're going to call f concave, I'll use a highlighter, concave up on an interval I if the graph of f lies above its tangent line, and we should add here on I. Okay? That's equivalent, and I'm not proving this, but I'm just telling you that's equivalent to saying f prime is increasing. Similar definition, we're going to call f concave down. Let's just do concave down on an interval I if the graph of f lies below its tangent line, and this is on I, which is the same as f prime decreasing. Finally, a word I haven't introduced before, f has an inflection point at x equals c if f actually changes concavity at x equals c. So let's scroll back up to our picture that we just drew. That point right there where we switched from the f prime decreasing to now it's increasing, that's the inflection point. So right here, this is an inflection point. And so you can kind of guess one of the things that's going to really interest us is how do we figure out concavity using calculus? And actually the answer is kind of on the screen in front of you. Notice that we've already identified, and I'm not proving anything, I'm not doing this rigorously, but for our purposes today, I've identified that, look, f is concave down. That's the same as saying f prime is decreasing, but we know what it means for a function to be decreasing. Any function g is decreasing when the derivative of g is negative. Well, the derivative of f prime is f double prime, and so somehow concave down means f double prime is negative, concave up means f double prime is positive, and that's exactly what the concavity test tells us. So before I work through the concavity test with you, I want to remind you, so far we have the increasing decreasing test, we have the first derivative test, and now we have the concavity test. And the concavity test says what we just said before. If the second derivative is positive on an interval, then f is concave up on that interval. If the second derivative is negative on an interval, then f is concave down on that interval. And so let's work out the same example that we've been doing throughout the course, throughout this video series. So we started with this nice, lovely cubic. We've taken its derivative. Actually, before we factored it, but I'll just mention to you, when you want to take the second derivative, it's easier to work with the unfactored first derivative. So f double prime of x is 6x minus 6, and I'm interested in knowing where is the second derivative positive or negative. And so I'm going to go ahead and make a number line. This number line is going to be for f double prime. I really encourage you, label your number lines with either f prime or f double prime. Otherwise, you'll start losing track of them. Please notice that if you solve f double prime of x equals to 0, or undefined actually, this one is defined everywhere. If I solve f double prime of x equals 0, then I get x equals 1. And I would also be interested in where the second derivative is undefined. All right, at x equals 1, then I notice, look, if I plug in something bigger than 1, the second derivative is positive. Plug in something less than 1, the second derivative is negative. And so now I can immediately conclude that f, the original function, is concave up. I'll usually abbreviate that with cu on the open interval 1 to infinity. And f is concave down on minus infinity to 1. And I also want to point out one other thing. F has an inflection point. You should be able to see where at the point x equals 1. And if I want to graph that, then I can plug in 1 into my function. So I thought it might be good for us, before we end this video, to go ahead and put all of this information together for this particular example and try and sketch a graph. Because, by the way, that is the goal. The goal is to be able to use this different information from the derivative to produce accurate graphs of our functions. Okay, so let's scroll down, and I've actually gone ahead and rewritten down the number line for f prime, although oh, there it is. I was going to say, I didn't think I broke my own rule. I was zoomed in a little bit. Looked like I hadn't labeled it there. So from the number line for f prime, and then I'm also going to go ahead and copy the number line for f double prime. We're going to paste those down here, not side by side, but let's get them where we can see them both. Maybe we'll move them up a little bit because they might be, whoops, they might be in the way for our graph. We don't want to be cramped our style at all. Okay, so here's the idea. It really helps if you will just begin by marking all the points of interest that you have. So you see that something interesting happens at 3, -1, and 1. So let's get green dots, and I guess I'll just work off of my grid here. Each unit is going to be 1. I'll probably have to scale this, so this will very unlikely be able to fit on my grid. I'll have to scale it some, but at least for starting, let's put a dot at 3, a dot at 1, and a dot at -1, and that seems to capture the interesting points. Now, for me to be able to actually use this information, I've got to have the corresponding f values. I have to have the corresponding y value when I plug those points in. So I'm interested in f of 3, and f of 3, let's go back and work it out. Unfortunately, I didn't work this out ahead of time. I should have, but we can do it. F of 3 is going to be what? 27 minus, oh, look at that, minus 27 minus another 27 plus 4. So f of 3 is actually minus 23. So again, that's not going to fit on my grid. I'll have to scale. F of -1, I believe, is 9, and f of 1. We did f of, no, we haven't done f of 1. Let's do, scroll up. F of 1 is what? 1 minus 3 minus 9 plus 4. So this is minus 12 plus 5 is minus 7. F of 1 is -7. So I'm really interested in not so much these green points. That's where that's the x values where things happen. I actually want to plot these points. So I think let's make blue our graph in remembrance of Mathematica graphs. That's the color that Mathematica would pick. F of 3 is, we're just going to go off grid here. We're way down here at -23. F of 1 is much, much closer, but it's still at -7. And then f of -1 is up here at 9, so we'll just kind of guess. I'm totally not to scale at this point, but that's okay. All right, so I'm going to go back and erase now the green dots, if I can, without erasing my axes, because what I'm really interested in are these points, and these are happening, these actual x-y pairs, where I plug the point of interest into f and get out a ordered pair on my graph. All right, so now what I like to do is remind myself that, whoops, I think I copied this wrong. I'm supposed to be plus, minus, plus. F has a local max at -1 and a local min at 3. So I'm just going to go over to -1, and I'm going to draw, I don't know what it looks like, but I know that it has a local max there. So I'm going to draw the slight picture of a local max. And over here at 3, I've got a local min. I'm going to draw that picture. I know that I've got concavity changing at this point, and actually I'm going to have to connect this graph to this one down here and go through that point, so somehow we can kind of figure out the graph's going to go like that, and we're going to change concavity there. Wow, if you wanted to, and this is a really big shift for you guys, if you wanted to, you could go back up to f and try and figure out where is f equal to 0. But that often is quite difficult. So I'm not always going to do that. Here's what I would say to you. If you can find the x-intercepts of the original function easily, do it. That's great. That's what you did in college algebra. That was the only thing we could do, was find the x-intercepts. But that often isn't very convenient in the problems that we're looking at, or it's just difficult. So I'm not always going to find that. In this case, I can see I'm going to have 3 x-intercepts. I'm not going to figure out what they are, too much work, but I'm essentially done. So the graph has to do this. It has to make that local min. It's got to come up and go through my inflection point, and I've got to get up to my other local max, and then I've got to come back down. I'm going to clean this up ever so slightly. Hopefully you're with me so far and you agree that our graph has to look like that based on the 3 points. Now, there's more though. Let me zoom out a little bit. F is increasing from 3 on. So from 3 on, this function does nothing but climb. So I don't know what the graph looks like exactly, but it has to just keep climbing and climbing and climbing. And the same thing, from minus infinity all the way to -1, F is climbing. So this is backwards. I'm going to draw it down, but remember, we actually move left to right. As you go left to right, the function is climbing, and then it's dropping, and then it's climbing. And so that is a relatively accurate picture of this graph, and the key points are all identified. Here's that inflection point. You can actually see the concavity changing. Here is the local extremas. I've captured the increasing and decreasing. And I've captured concavity as well. I can see the concavity. I'm concave down from minus infinity to -1. I'm concave up from 1 onward. So that is a first example of curve sketching. I want to, in the next video, show you another test that will allow us to test for local extrema. I'll probably keep that one short, and then I'll end with one final video for this lecture series where I will work out example from scratch with you, and then we'll graph it.